Okay, so last time we were talking about graphs of multivariable functions. So it's one kind of a picture that you can draw of a multivariable function. It's a familiar construction. You take the input variables, the output variables, right? You put them into the same little world. In this case, if we have two input variables, and if you have one output variable, notice that gives you points that are in R3. The weird thing, right off the bat, the weird thing about graphs is they don't live inside of the domain. They don't live inside of the target. They live inside of a brand new space that we make up for its purpose, right? It's kind of weird. It's certainly a manufactured construction, and it has a lot of great things about it, right? But you might have noticed in a single variable calculus class that it was a little weird. That it's single variable calculus, but we're drawing two-dimensional pictures, right? And that, again, is because you're combining the input variable and the output variable into one picture. Okay. All right, so when you have multiple input variables, you're going to get an even higher dimensional picture, such as, for example, here you get a three-dimensional picture. I'll also point out that however many input variables you have, that tells you the dimension of your domain, which you can kind of sort of see as the, if you will, a part of the space that the graph lives in. And for every point in this, let's see, we have two input variables here. For every point in this two-dimensional domain, if you will, we get a corresponding point on the graph. Right? So the graph itself lives inside of a three-dimensional world, but it has the same sort of dimension as the domain. So this graph, for example, this is a surface. It's a two-dimensional thing. It lives inside of a three-dimensional world. Yeah. But the surface itself is two-dimensional, and that's because every point on that graph surface itself comes from a point in the domain, and the domain is two-dimensional. Okay. All right. Okay, graphs are familiar. This isn't that different from how we drew graphs back in single variable calculus. So that's nice. They're also very limited. We cannot do multivariable calculus living only with graphs. They're just not good enough. There's some major flaws and shortcomings to graphs that we're going to talk about in a couple minutes. So I just wanted to point that out. In single variable calculus, pretty much every picture you ever drew, few exceptions, but the vast majority of pictures you drew in Calc 1 classes, they're all graphs. And that's fine because single variable graphs are wonderful. Right? There's some big problems that we're going to face going forward. Okay. All right. Next kind of construction that we're going to talk about is called a level set. This is a different way to turn a function into a picture. It's not a graph. Very importantly, not the same as the graph construction. Please don't use the word graph as a kind of a catch-all, kind of like any kind of a picture, sort of a synonym for picture or figure. Right? Graph is a very specific construction that we talked about here. Right? So level sets are not graphs. They are not a different kind of graph. They are a different kind of picture. Okay. So the idea is if you have a function. By the way, we're going to look only at real valued functions, just R1 outputs. You can take that function, and instead of setting the values equal to a new variable, y, we're going to set the values of the function equal to a constant. It gives you an equation. It's a different kind of an equation. Right? It's importantly different from the equation that defines the graph. And it gives you, therefore, a different kind of a picture because this picture has different kinds of solution sets. So I'm going to show you some examples of where y'all have actually seen level sets before. Maybe not with that terminology. But if you've ever gone hiking, and if you ever looked at a map that has what they call contour lines, or Google Maps these days calls it the terrain. I forget exactly how to do it, but at a certain level of zoom, there's an option that you can hit terrain. It'll show you contour lines. Right? So the idea is that these are lines of constant altitude, right? So every point on that line has the same altitude, and then every point on this curve has the same altitude, and then etc. Every point on this curve has the same altitude. And you draw a picture like that, and it helps you understand the shape of the mountain that you're looking at, or that you're hiking. Right? That's nice. Okay. This is a level set. It's a level set of the altitude function, right? So for a given longitude and latitude, right? There's longitude, there's latitude. Given a longitude and a latitude, there's a corresponding altitude. And if you set that altitude equal to a constant, then again, that's where level sets come from, right? These are the points where that altitude is equal to a certain constant. Okay. Right. So here's another example. I'm just going to come up here where I have some space. If you've ever... Well, I used to be able to say in teaching this class, you used to be able to say, if you're ever watching the weather, and I don't think anyone really does that anymore, at least y'all's generation, right? Old people sit there and watch the weather on TV, right? But y'all mostly go to weather apps, I suppose, right? Anyway, whether it's on the Weather Channel or weather apps, if you look at the way they describe temperature, what they'll do is they'll have certain lines going along, and then they'll have colors in between, right? So this is maybe the section that they'll label as in the 70s. The temperature is in the 70s. And so they'll write, in here, 70s. And then it's a little bit cooler further north, let's say. Right, so this they'll label as the 60s, for example. Right, y'all have seen these kind of pictures somewhere or another. So you're actually looking at level sets. So specifically, let's look at this curve right here. That curve, that's the line between the 60s and the 70s. Well, what value is it that's between the 60s and the 70s? Well, it's 70. Right? So this is where the temperature function is equal to 70. And let me write that a little bit differently. Don't forget, temperature, among other things, is a function of position. It's a function of longitude and latitude. So that's where your temperature function of position is 70, 70 being a constant. We are therefore looking at a level set. Right? We have set equal to a constant. We're looking at a level set of that multivariable function. So anyway, I think that's pretty relatable, and so level sets are proved to be convenient ways to represent certain kinds of things, right? Understanding temperature, understanding the shapes of mountains and such. Okay. All right. And I'll talk about why in a couple of minutes. So first observation I want to make, though, about them is how they relate to graphs. Now, they're very different from graphs, but nevertheless, there's a nice connection between them. So, reminder, if you have a multivariable function, right, let me use a different color. Let me use purple. You have a multivariable function. A graph of that function is what you get when you set that function equal to a new variable, like we've used z here, and then you draw the solution set to that resulting equation of, in this case, 3 variables. Same function now, same function. A level set is what you get when you set that function equal to a constant, not a new variable, constant. This then gives you, in this case anyway, an equation of 2 variables. So that's a big difference, right? Graphs give you equations of, in this case, 3 variables, whereas level sets only 2 variables. So they're different. What's the connection between them? The connection, you'll notice that if you take this graph equation, and if you just tack on an additional equation, if I just say, let's look at z equals c, the combination of these 2 equations, you can not too challenging, eliminate the z, and realize that, in fact, what you're looking at is exactly a level set. That's kind of weird, right? So tacking on this additional equation turns graphs into level sets. And what is this equation? This is a cross-section, right? We talked about that a couple lectures back. This is that whole business about taking horizontal slices, for example. So that's the neat connection that I want to point out. And that is that level sets are algebraically almost indistinguishable from looking at cross-sections of graphs. Right? Level sets are cross-sections of graphs. I'm going to put an asterisk on that. There is one little distinction I'll make in a couple of minutes. We'll get to that momentarily. Okay, first let's get our hands dirty. Here's an example. Let's look at this function here. It's a function of two input variables, real valued, so one output variable. We've seen this function before. Nice to have a familiar starting example, right? Let's draw level sets of this. Right, so this function, there it is. Level sets are what you get by setting it equal to certain constants. And notice that this equation that you get by setting f equal to various constants, that equation is going to give you a bunch of circles. Okay, no big. Everybody happy with that? Is that cool? Yeah. Okay. On the other hand, what if I wanted to do a graph now of the same function? Same function. Still R2 to R1. X squared plus y squared. That same function. A graph is what you get when you take that function, same function, graph, you set equal to a new variable. In this case, let's pick z, alphabetical order, whatever, right? That gives you an equation, and if you draw the solutions to that equation, well, this is another old sort of familiar thing. This is an equation that we've studied in the past, and that equation is a paraboloid. So let's look then at these two different pictures we've got. These are two different pictures talking about the same function, right? It's still this same function here. F of xy equals x squared plus y squared. Two totally different pictures. But you can see in here what the connection is between these two pictures. So these two constructions, the graph construction, the level set construction, the relationship between them is that, and again, we have geometric intuition for this. If you take a horizontal cross section of the graph, you get a level set. Circle in this case. Everybody on board? Yep.
So each one of the so-called rings in the level set would be for a different value c?
Yep, that's right. So let's, for example, if I were to go down a little lower down here, take a slice. Right, we're going to get a slightly smaller circle, which is going to be like that. Totally. Okay. All right. Now here's the asterisk. I like to. It rolls off the tongue nicely to be able to say level sets are cross sections of graphs, and you see what I'm talking about here. Now let me correct the. To be precise, cross sections of graphs live in the same world that graphs live in. This cross section of this graph is a circle, but it lives inside of R3. It's sitting up here in space, right? This level set is in 2 dimensions. It is not sitting up in space or anything. It's just in R2. So they're not technically the same, but they have the exact same shape. They're described by the same algebra. It's just that same algebra that describes them both as a level set, it's describing a set in R2. In the graph context, it's describing, that same shape, but sitting up at a certain altitude inside of R3. So they're not technically the exact same thing, but this is a really sort of subtle fine point, and you'd be forgiven for not caring about that. Okay. All right. Okay, so now I want to talk for a moment while we're here on this picture. This is exactly what I need to make an important point. I emphasize you got to be really, really careful going forward about language. It's really easy to mess this up, especially when you're new to these kinds of things. And especially when in single variable calculus classes, there's really kind of nothing to worry about along these lines because every picture you're looking at is a graph. Right? And so in a single variable calculus class, you can just say graph interchangeably with picture. You're usually right in a single variable setting. Right? And so students will develop a lot of sort of, I'm going to call it sloppiness, of bad habits, due to the fact that nothing bad happens. Right? And now we have to start being more careful. Now, not all pictures are graphs. And it's importantly the case, right? So this picture right here, that is not a graph of this function. It's a level set. Level set is not a graph. A graph is not a level set. Different things. If you want to say these are both pictures, okay, sure, right? I got cut off by the bottom of the screen there. These are both pictures. That's true. They're both figures, I suppose. But be real careful with the word graph and with the word level set. Okay. All right. Here's another point to keep in mind. Why do we have to be so careful? I mean, if I say level set when I mean graph, I mean, who really, come on, what's the big deal? We're about to start doing calculus. Right? And no surprise, I hope, calculus has geometric interpretations. Okay. So, for example, if I look at certain kinds of derivatives, right? Well, in the context of level sets, in this picture here, what do those derivatives look like? What's the geometric interpretation of derivatives in the context of level sets? Well, we're going to have certain interpretations. So let me say geometric interpretations of level sets. So this connection. This is what I like to call the calculus of level sets. Calculus of level sets. That means that what are the connections between the algebra of derivatives and the geometry of what does that relate to? Okay. So the calculus of level sets is just different from the calculus of graphs. Right? If you look on this, if you look on the graph context, those same exact derivatives in this totally different picture, well, of course the derivative is going to have a different geometric interpretation. I mean, of course it is. That's what I mean. Wouldn't it be stunning if it weren't different? Right? The picture is totally different. So the calculus of graphs. The way we relate derivatives to what they look like in the graph setting, totally different thing. So if you're sloppy about the distinction between a graph and a level set, then you're going to be sloppy in your interpretations of derivatives, and you're going to come up with a lot of wrong answers. And I've seen it happen so many times. And I've been teaching this class now for, let's just say, a long time, right? So I started to notice early on that this confusion of, the different geometric constructions, conflating these causes students to conflate these. So be real careful about it. Here's an example to help you make the distinction, sort of coming at this from a different point of view. Let's look at this plane. Here's the equation of a plane, right? Chapter 12 observation. And is this plane a graph of something? And if so, what is this a graph of? Now, it's so easy to just mess up on this and just think, it's a graph of, I don't know, that. Or, to conflate an equation with a function. Very importantly, this thing that I've just circled there, that's not a function, that's an equation. Right? This is a function. That's a thing that if you give me an x, a y, and a z, then out comes a number. That's not what this is. This is a statement about existing x, y's, and z's and how they have to relate to each other. So make sure to distinguish between equations and functions, right? So what function is this a graph of? Well, what I've got to do is I've got to figure out, and let me sort of scratch out the answer here. What I've got to do is figure out some function whose graph, keep in mind the graph is what you get when you set your function equal to a new variable, let's say z. What can I fill in here? What function is it that if I set it equal to z gives me this plane? Well, let me remind you, the plane P is described by that equation. And so if I want to get that plane, what that means is I need the resulting equation to be an equation that's equivalent to what I've got there. If it's going to be equivalent, then I need for this z to be the same as that z. And said differently then, the way to fill in these blanks, the way to figure out what is this function that when I set it equal to z gives me that plane, I just need to solve for z in the equation of that plane. And that's easy algebra. Y'all can solve for z in the equation of that plane. You get this. And so now it's really easy to see that this equation I've got down here, that equation is clearly, right, no problem, clearly equivalent to that equation up there for the plane. And furthermore, this equation that I've got down here is clearly the graph, right? That's what a graph is. That's the graph of some function. So here's a formula for this function. Notice, by the way, this function here that I just wrote down, that function is a function of x and y. Everybody on board? Everybody see how that worked? Okay. Now, analogous analysis. If I want to take, again, same plane, is this a level set of some function? What function is this a level set of? Well, I've got to figure out if I want this to be if I want this to be a level set of something, then there needs to be something. There needs to be something. Let's figure out what that is. That when I set it equal to a constant, I need to get that this resulting equation is the same as that equation. So what can I set equal to a constant to give me 2x minus y plus 3z equals 6? Well, conveniently, 6 is a constant. It's kind of already in the desired form, and so it's pretty easy to see that that is the thing that does it, right? This equation is obviously the same as that equation. Just choose c equals 6. Right? And no problem. Notice that this function that I just wrote down is a function of more than just x and y. That's a function of x, y, and z. It's a function of 3 variables, not 2. Okay. All right, so you got to be real careful about this. Now, this will give what I think is maybe an easier to see example of how you can be steered in a terribly wrong direction if you conflate the calculus of level sets with the calculus of graphs. Right? If you're looking at this plane and you want to understand a certain thing about it, what you're going to do, right, is you need to take this geometric thing with an equation, right? You're going to have to figure out what function am I looking at. Well, it depends. If you want to view it as a graph of something, you're looking at this function. But if you want to view it as a level set of something, you're looking at this function. So, do you want to do the calculus of level sets, or do you want to use the calculus of graphs? If you want to use the calculus of graphs, you have to use the function for which it is a graph. Get 2 seconds. If you want to use the calculus of level sets, and by the way, there's some really cool stuff that we're going to see about the calculus of level sets. If you want to use that cool stuff about calculus of level sets, you got to use the right function. And if you apply the calculus of level sets to this function, your answer is going to be dramatically, catastrophically, like posted on Reddit, bad, wrong, right? So you got to be real careful about that. Yes. Nope. So here are 2 different pictures, right? One of these pictures is a level set, and one of these pictures is a graph.
Both of them are functions.
Both of what now?
Both of the equations are functions.
Equations are not functions. Yeah. So equations are statements. Functions are actions. A function is a thing that does something. An equation is just a statement about two things on either side.
So if we draw the picture of a function, is that picture?
Okay. Now, so picture of a function. Which picture? Do you mean the level set picture or the graph picture? So this is the thing, all right? So you're stuck in this. I totally get where you're coming from, right? Most of the students in the class are probably still working through these same sort of like, we're distinguishing things that there used to be no need for such a distinction, right? But so this is what you've got to be real careful about. When you say graph going forward, don't just think, it's the picture, Come on, it's the function. No, it's a very specific kind of picture, yeah. And level sets are a different, very specific kind of picture. Yes?
How do we determine whether we use the calculus of level sets or calculus of graphs?
It depends on the situation. It depends on what you want to know. It's hard for me to answer that question without my having told you already what is the calculus of level sets. What is the calculus of graphs? We'll get to that when we get to it, right? It's going to be a little while. But what you're going to notice is that, when we've talked about these two different connections, right? Certain things are like, come to think of it, the thing I need is exactly one of these objects that's discussed in the calculus of level sets. So let me interpret my plane as a level set, and let me therefore use this function. Yeah. So the cues that you're asking about will come from understanding what these connections are. Yeah.
Would the level set with 3 input variables be in 3 dimensions?
Yep.
It would? Okay.
Yeah. I'm going to show you an example of that in just a minute.
Okay, right.
Yep. Totally. Oh, yeah. It's really confusing. Yeah. So do notice along the lines of your observation here that here we're looking at a single function, and the level sets and the graphs. Not only do they look different, they live in different worlds. Right. The level set of this function. Level sets, plural of this function, live in R2. The graph lives in R3. Yes?
So going back to the equation from the example.
This example here?
The 2x minus y plus 3z equals 6. We had equations like that in the homework from Monday.
Okay,
and
yep.
They were, it said graph them.
Oh yeah, I know the book it really bugs me, but the book uses the word graph. Sorry, I should have mentioned that. The book talks about graphs of equations, which is just, oh my God. Technically, there is no, my proposal is that the word graph of an equation should have no meaning at all. Right? Because I want to reserve the graph word to mean this specific construction that we're talking about here. Right? I think it's confusing for the book to talk about, to give meaning to the phrase graph of an equation. Yeah, but they do, and so let me just say, every time you see in the book when they say graph of an equation, just kind of roll your eyes a little bit and think, what they should have said is solution set to an equation, right? And then just go ahead and interpret it in the way that they intended and move on. Yeah.
So were we really drawing level sets?
You were drawing solution sets to equations, and in a way you were drawing level sets, but I haven't gotten to that part yet. Yeah. Okay. All right, here's another example, by the way. This one's a little easier, a little harder, depends on how you look at it. Here we're just looking at a line. This is a line in R2, right? Algebra 1, right? The good old days, right? But look how many different ways I can relate this simple little line to different functions. And I'll let you walk through the details on your own, but this is a graph of that function. It's a level set of this, let's recognize, very different function, right? And it is parameterized by this third, very different function. Now, we've got 3 different functions there, right? The calculus of these 3 different functions are going to be totally different. They're describing the same line. So again, if you use the calculus of level sets on the function whose graph you're interested in, then it's a catastrophe, right? And if you use the calculus of parameterizations on a function whose level set you're looking at, and again, it doesn't make any sense at all. By the way, we've already talked some about calculus of parameterizations, right? Derivatives of parametric curves give you velocity vectors. That's a geometric interpretation of something that we've described of an algebraic thing, namely derivatives. So that's the kind of thing. So the calculus of parameterizations we've already talked about somewhat, and we're gonna do more with it later. But there's more to come on calculus of level sets and calculus of graphs. Okay, last question. We got to go on. Yeah.
Is the dimension of level set not always one less than the dimension of graph?
We're only going to talk in this course about real valued functions. Correction. We're only going to talk about level sets of real valued functions. In that being the case, yes. And the reason why, I don't want to get into it, but yes, it's true for exactly the reasons you think it's true. Yeah.
So level set is one dimension less.
That's right. And a level set has the set itself is of dimension that's one less than the dimension of the domain that it lives inside of. Yeah. Okay. So here's a neat fact. And now in order to talk about this fact, we have to be very careful about this distinction between graphs and level sets. This is something that this is a true and important statement that you can make if you're careful with the distinction between graphs and level sets. And here it is. Every graph is, in fact, a level set of a different function. Not the same function, of course, right? But every graph is actually a level set of a different function. This is actually easy to prove. It comes from noticing that these two equations here are, totally equivalent, right? Those two equations both, all I did is I took the right-hand side and I whipped it over to the left-hand side, right? I hardly did anything. But notice what we're looking at in the top equation. We're looking at a graph. Let me do it like that. We're looking at a graph, specifically a graph of this function f. Here, let me circle it like this. It's a graph of this original function that we were given from Rn to R1. That's the graph of that function. But the same exact equation down here in purple, right? It's slightly in different form, but morally the same equation. That same exact equation is a level set of this function. Right? It's just an observation. Level set means take some expression, set it equal to 0. Now you're looking at a level set of the function that you set equal to 0. There it is. Right? So every graph is a level set. Now, I know that I can always do this because in order to do this, all I need to be able to do is to take what's on the right-hand side of an equation and subtract it over to the left-hand side of the equation. Of course you can always do that. Right? So if you ever see a graph of something, you can reinterpret it as a level set of something else. And here's an explicit example. Just to get our hands dirty. So, here's a function. Let's look at a graph of this function. Right, here it is, that function there. We're looking at a graph of that function. We pull this little algebraic fast one. It didn't really hardly do anything. Just moved everything over to the other side of the equation. And now we are looking at a level set, you notice, of this function. So, how would you use this? Well, again, we haven't learned yet about the calculus of level sets and the calculus of graphs. But if you found yourself looking at this graph, right, there's a graph, But if what you need, if the thing that you need to understand is you know that you could get the thing that you need if you could just view this, if only this were a level set instead of a graph. Okay, cool. Now it's a level set. It's just a level set of something else. And you can then use the calculus of level sets, which we will talk about later on, to answer your question. Okay, so this is a nice little fast one to be aware of. This gets used a lot later on in the course, so definitely want to make sure that you're clear on how this little. It's a little slick move, right? I mean, not much happened. Arguably, all I did is a little bit of Algebra 1, but that allowed us a very sophisticated reinterpretation of the question. Okay. Now, I want to point out that this does not go the other way. It is not true to say that every level set is a graph. If you try to turn this around backwards, it just doesn't work. Right? Easy example. There's a level set. Right? That's a level set. It's not the graph of anything. Fails the vertical line test badly in both directions. It's just not going to happen, right? There's not a graph at all in any sense. And roughly speaking, the point is, you don't have, I mean, if I wanted to turn this algebra around backwards, I would need for there to be something that I could solve for. That something that I could solve for was right there. In this case, here, what would I solve for? I can't really solve for anything because of the squares. And you just, plus or minus doesn't count, right? So you just can't solve for either x or y. Okay, so this is a one-directional thing. And this is really arguably a big argument in favor of why level sets are awesome. Level sets are awesome. The calculus of level sets is awesome because even if you're not looking at a level set, you can make it a level set. It's, in some sense, always on the table. The calculus of level sets is always something that you can take advantage of. All right. Here's another reason that I like level sets. It's what I like to call dimensionally simpler. We've already kind of hit on this point a little bit. Let's do it again. Here's a function. That function, on the one hand, we can look at the graph of that function, and the graph. This is a problem that y'all can play with on your own. Think about cross sections. It's a good exercise. But the graph is going to be kind of a tilted trough sort of a thing. The level sets, on the other hand, the level sets set equal to a constant instead. Well, those are just parabolas. Different values of c give you different parabolas, but much easier to draw. Right? Two-dimensional picture instead of a three-dimensional picture. Three-dimensional drawing's hard. Right? There's nothing wrong with wanting to avoid unnecessary effort. Right? This long and glorious tradition in math of trying to avoid effort. Level sets are nice. Yep.
Could you also, try to figure out what the level set, what it looks, you could set it equal to y?
No, because y is not a constant. Very importantly, you got to set it equal to a constant.
Graphing it, because when you graph equations, when you graph regular parabolas, you have x and y.
So that's a crutch. So don't rely on this idea that this is always x and this is always y. I mean, if you decided that you want to look at level sets, right, this right here, that says that you're going to take whatever function you're interested in. Level set means I'm going to set it equal to a constant.
I know, but if you rearrange it to c minus x squared, that would give you the...
Look, how you analyze this resulting equation is up to you. Knock yourself out. I misunderstood your question.
I was saying y equals c minus x squared.
So there you're not really technically doing anything if you're just moving things around within an equation. Perfect. Yeah. So knock yourself out. Yeah. Whatever makes it easier for you to see. Yeah. Totally fine. Right. Sorry, I misunderstood your question. Okay. Here's another thing I want to point out. A lot of students say, here's my problem with level sets. The problem with level sets is, look, I can only draw so many of them. Right. There's one of them. here's another one, here's another one, but I've just left this great big gap in here. What's going on in there? My picture does not address at all what's going on in there, or anywhere down here, or anywhere up. There's just so much missing from this picture, you could argue. Right? Level sets are kind of bad at that. Give me a second. So here's my counterpoint to that. First, yes, I recognize there's a lot missing in this picture, but here's the thing. There's a lot missing in this picture too. Right? What did I actually draw here? I actually drew just that, right? I didn't draw anything to tell you what's going on here. Now, I kind of conned you into believing that I did, because by drawing those lines that I did, I've planted a thought in your mind that there's a surface there. But that's your imagination. Right? And it's a good, I'm glad that I can manipulate your minds in that way, right? And it's useful for you to manipulate your own mind into thinking something's there that you didn't draw at all, right? But so it remains. This graph picture is really, really short. And furthermore, I don't know if y'all ever seen those things where I've been looking at fun stuff on social media recently, and they have these artworks where if you look at that artwork from a certain perspective, it looks like a whatever, but then if you turn your head around, it's like, oh my gosh, it's a totally different thing, right? And they do that by when you're looking at it from one perspective, you can't tell how far it is away. Depth perception's not there, right? So same deal here. How far is that away? Is that where I think it is, or maybe it's a lot closer to us and there's just some weird depth perception thing going on. So that is not addressed at all in graphs, right? I am, again, sort of relying on you interpreting the way I want you to interpret it. And that's not true of these level sets here. These level sets I'm drawing exactly in R2. I'm drawing a two-dimensional picture on two-dimensional paper. I can't con you in that way with this picture. Yeah, you had a question.
I guess then why, when you do draw the level sets, why do you draw 3 and not
Why do what?
why do you draw 3?
Oh, it's just a sort of a compromise. I can't draw infinitely many.
Yeah.
I just don't have that kind of time, right? But I figured one isn't really enough. So you draw enough until you feel like I see what's going on here, right? But there's no magic right answer to how many level sets to draw. Does that make sense?
Yeah, because in visualizing it, the level set for the on page 49, that, I think part of the confusion there was that if virtually every single C accounted for, wouldn't it just be
That's the thing. Yeah, if I were to draw all the level sets, the picture would just be solid black.
Yeah.
Yeah, I could just go buy black construction paper and see, look, I drew all of the level sets. Right? Yeah, totally. Right. You had a question. Yeah.
Could you draw the level sets of C equals x squared minus z?
C equals. Okay, so you're talking about you want to draw level sets of a function, and you didn't give me a function. You gave me an equation.
With this function.
Okay, so this is your function. Okay, now what do you want? You want to draw level sets of it?
Yes. So
the level sets.
Flip around the various.
Well, so I think you may be asking something similar to what he asked. This equation is totally equivalent to if you want to rewrite this equation as y equals c minus x squared. If you prefer this to this, whatever, they're the same.
Well, I was thinking, if you look at the graph, and if you just, sliced it with respect to the different...
Well, now you're changing. Now you're talking about now you're taking cross-sections of the level set. That's a different thing.
So level sets can only, can only be, x and y.
Well, a level set. Statements that have the word always in them scare me because I don't. What are you willing to? Always suggest that there's a bunch of things you're going to change, and you want this fact to remain fixed. And I don't know what you're talking about. Maybe changing. So always in what sense is
in this function, only the independent variables can be shown on the levels. Level sets live inside of the domain.
Yeah, right. So the domain is the world that the inputs to the function come from, right? And you're quite right that level sets do live inside of the domain. Yeah. Right.
Yeah, thanks.
Cool. Okay. So there's some big downsides, right? I mean, this is one of the unfortunate things about graphs. For one, here's another thing. I'm trying to con you into believing that there's a three-dimensional picture there. But come look over here. You can see it's really totally two-dimensional, right? That is absolutely a flat screen, right? This is not actually coming out of the screen at you. Right? So it's a two-dimensional picture in which I'm trying to con you into believing that you're seeing a three-dimensional picture. So that's kind of lame, right? It's certainly suboptimal. And I could make a three-dimensional model, but that's really inconvenient. 3D printers work slow. Right? You only use a 3D printer on your homework. Right? So anyway, the graph picture is not to be put up on a pedestal. Here's another example, and I'll just be real quick with this one, but here's a perfectly innocent function. There's only 3 variables. It's just 3, right? It's not 7, right? It's just 3 input variables. And this function, if you were to try to draw the graph, right, how do we draw a graph? To draw a graph, we have to set that equal to a new variable. Maybe I'd call that new variable W. This equation has 4 variables. I would need a 4-dimensional picture, and I can't do that. So this fairly innocent little function here, you simply cannot draw the graph. It's not on the table. It's not possible. Nobody can do it. You can't even really visualize the graph. You can't even really visualize 4 dimensions. Right? So this graph construction's got a lot of flaws, and whereas this same function, if you want to draw the level sets come from setting equal to a constant. This equation has 3 variables, and yeah, they're kind of hard to draw, and there's disadvantages of these pictures, and it's a 2-dimensional representation of a 3-dimensional thing, and there's these great big gaps where I didn't really do anything, and it's imperfect, but it's better than nothing, which is what I've got over here, right? So anyway, I'm trying to make the pitch that level sets are important, they're useful, and you should be interested in developing intuition and familiarity with level sets and keeping it distinct as a concept from graphs. Yes?
So when we have equations that already have 3 variables in them,
Yeah.
when we want to do the calculus of level sets.
Well, you'd better, because otherwise you're talking about a 4-dimensional picture, yeah. But that's not the only time. I mean, there's plenty of situations that we'll see later on. And again, it's hard for me to talk about what's going to happen in the future when I haven't told you yet, right? But there's going to be situations where this point of view is going to be really useful, and this one not so much. And that's just going to have to wait. Yeah. Okay. So we've got a couple of minutes here. No, we don't. We have 20 seconds. Oh. All right. We'll call it right here. And see you all on Friday. Have a good day.